Hello. I've already said hello to the person who's here, but for you who's watching this in the future, hello to you as well. I'm David. I'm the coordinator of the Maths Learning Centre at the University of Adelaide, and this is a revision seminar for Mathematical Economics 1 in Semester 2 2022. And today we are talking about integrals. As soon as I remember how to do this. All right. Okay. So I think I actually have that's on the screen. So integrals is half of calculus. There are derivatives and there are integrals. And they are two different flavours of calculus. And calculus is all about, has two features. One is about finding out about how things change and either figuring out how quickly they change or figuring out the total of the change. They're the two different, that's one side of it, and the other side of it is finding information out about functions and solving problems about maximums and minimums and those sorts of things. So calculus can tell you most of the things you want to know about functions and their graphs and their behaviour and when their maximums and minimums are and areas under them and all of those things. So that's all of that. That's what calculus is for. And so this course has had a fair bit of calculus. There's differential calculus, and now we've got integral calculus. So the reason it's called integral is because of the word integrate in English. Integrate means, in English, to join together into one whole. And talk about people integrating into society, like immigrants arriving in a country and integrating in society, and then society joins together with the new people and become a new and better whole. That's the idea of what integrate means, and the reason that is what it's called is that integration and integrals are designed to take like a running total of a function and join it all together into a total. So if you've got a function, and this is a traditional graph of a function, and every x has a function value to go with it, something like that. And if you somehow combine all these together into a sort of a total, that's what integration is designed to do. Yep. So it's some sort of total of the function values across all the possible x's, taking into account how often each function value happens, like how long a function spends being a particular number. And there are two kinds of integrals, and the definite integral was the one that was invented first. So I just want to talk a little bit about that first. The definite integral is what this is about. So the big idea is if you have a function that spends all of its time being the same number, here maybe it starts at 5 and it goes to 20 and it has height 3 maybe, then so I've got f of x equals 3. So that's my most fundamental bottom easiest to figure out example. So my function is 3 for every number between 5 and 20. Then what I'm going to do is I'm going to add up this area, and that will be what the integral is. So it spends a gap of 15. It spends a time, I'm going to call it time. It spends a time of 15 being the number 3, and so it's 15 times 3. This is how wide it is, and this is how high it is, and so the total is 45. And it's essentially areas, that's the idea behind it. But the point is that if a function spends a lot of time being negative, so this function something like that, then the integral here, it spends a gap of 2.7 being minus 2, and so the answer is whatever that is. And so in this case it's this wide, but it's this deep. And so it's minus, I really shouldn't have given myself weird numbers like 2.7. 2 times 0.7 will be 1.4. It will be minus 5.4. So this is what it's all designed upon, this idea that if I wanted to have some sort of total of what this function was across this zone, it spends all of its time being minus 2, and it spends this much time being minus 2, so I multiply them together. How do you feel about that? Okay. So it's sort of like the bit you would do before you do an average. So when you do an average, you add things up and you divide by how many there are. This is me saying, well, on average, this function is 3. If I wanted to know whether a function was on average 3, just give me a second. This function spends half its time being the number 4 and half its time being the number 2, and so on average it's 3. And so the idea is that if I added up this area and this area and divided by 2, that'd be the average. That wouldn't be the area. If I, 4 plus 2 divided by 2 is 3, that's the average. I can say that this function on average spends its time being 3, and so the integral is designed to be that total you get before you do the average. So you would go integral of this one would it spends 2 units of x being 4 and 2 units of x being 2, and so the total is 8 plus 4, which is 12. And the average is the total divided by the amount of space that I was using, and the amount of space that I was using was a width of 4. Yay, which makes sense. And so I can imagine functions that spend more time being one number than another. So if I had a function that spent twice as long being 4 as it did being 2, like that, then on average the average should be closer to 4 than it is to 2. And so this one, the integral, would be a gap of 4 times a height of 4 and a gap of 2 times a height of 2, which is a coincidence that they are the same numbers, I'm sorry. And this one would be 16 plus 4, which is 20. And the average would be 20 divided by the total width, which was 6, which is whatever it is. Closer to 4 than it is to 2. So that's one of the big ideas of what integrals are trying to do. They allow me to average out functions across space, but they also allow me to calculate areas. And that's all well and good for functions that are nice and flat like this, but how do I figure out for functions that are curved, which is almost all functions that we're actually interested in are curved and not flat. I mean, even a straight line isn't flat, but I could imagine it as an area as well. Yeah. So the notation for this sort of thing, just while I was here, if I called this function f of x, the notation for this integral would be this s, and this is a long s, the integral sign, the integral from the number 1 to the number 7 of the function f of x dx. And the pieces here that we're talking about are this dx, see this f of x times dx, that's going with the width and the height here. That's my height or depth. And that's my width there. And this is the options for x. So that's what the symbols mean, and you read it aloud as the integral from 1 to 7 of f of x dx. Okay. So what if I did have a function that was curved? I'm skipping, I'm not putting, you can start at 0, I'm just not doing that because then I can see where the edges are in my pictures. So what if I had a function that was curved? That would be a lot trickier because the only thing I know at the moment is how to deal with it when they're flat. But if I zoom in very close to my function with a magnifying glass, it'll look like this. Maybe not quite that sloped. That's about right. And I know, I'm actually going to zoom in down here as well on the x-axis that goes with this spot. Like that. I know that this space here, this area, which is the running total that I'm working on, is somewhere between these two. There's a slice that goes from here all the way to the bottom, and a slice that goes from here all the way to the bottom, and those two, this slice of area is definitely between those two, and I know how to figure out those because they're nice flat-topped rectangles. And if I make my distance this way on the x-axis really small, then these two should be really close to each other. And so my area will be squeezed neatly between them, and I'll get a nice, good idea of what the area really is. And so the dx that is being referred to in the function in the integral notation is this distance here, a very small distance on the x-axis. The d stands for difference, but it might as well stand for distance. And the f of x is sort of like the middle height here. Like that. So if I'm at position x on the x-axis just here, the height is f of x. And if this really was a straight line, as it looks when I'm zoomed all the way in, then this triangle here would fit neatly in this triangle here, and it would be the correct answer for the area. And so the idea is that I'm going to add up a whole lot of all these little f of x's. At each position x on the x-axis, I'm going to multiply a whole lot of little f of x's times by how far apart they all are, and then I'm going to add them all up. And the options for x go from 1 up to 10. And so that is the same idea as what we were doing before. Yep. And if I make these little gaps very small, it will be very close to the correct area. And as mathematicians, we imagine making them infinitely small, and it all works out because 400 years ago, a couple of mathematicians figured out a very useful relationship that tells us everything we need to know about this. How's that for you? Okay. Right. But in practice, we don't do this. Now, if you went to a machine like Desmos or GeoGebra or some other graphics calculator, and you asked it to find a definite integral for you, this is essentially what it's doing. So let me show you something. Take me a while to set it up. All right. So here is a function. It's probably not important what its formula is right now. And here is the integral I want to figure out. So the running total from 2 to 6. And I can get it to colour that in. But if I ask it to calculate it, it gives me the answer 16. And what it has done is sliced this up into very skinny slices and added them all up. That's what the computer has done in order to calculate that integral. Yeah, and it's done it very accurately. It's probably come out as 15.9999999 or something and rounded off to 16 for me. So that's pretty much what the computer has done. But you personally don't have to do any of that today. You may learn in future courses ways of doing that accurately if you don't have the actual formula for the function, but today it's just a theoretical idea that you can use. With this function, actually, you can see that this bit at the top, bump at the top, can be sliced off and fit into this hollow in the bottom, and that's what makes it 16, but it's not usually so accurate. example is not nearly so accurate. It comes out as 22.4. It's not like there's a piece that you can slice off and fit into another bit to make the area what you want. Yeah. Okay. Actually, just one more moment. I just want to do something on this graph again. All right. Okay, so this thing that I've coloured in here is a slightly different function. It goes above the x-axis and below and above again. And when I calculate the running total, as I move along here, starting at 2 and moving along towards 3 and 4, running total gets bigger and bigger and bigger, and then this bit below counts as negative, and so the running total will get smaller again, and then it will start getting bigger again here. So this bit below counts as negative, and we've got a total area of 4, and that's because this big bit here and these two blue bits count as positive, but the purple bit counts as negative, and it'll make the answer a bit smaller. And if I was very careful, this area, this integral, comes out as the answer 0 because the bit above neatly is exactly the same as the bit below, and so the running total as I go from 2 to 6 actually comes out as 0 because it spends just as much time above the x-axis as it does below. How do you feel about that? Cool. Right. Okay. So all of that was definite integrals. So if you've got a function whose graph is made up of neat straight lines, then you can figure out definite integrals by calculating areas, if you want. If you draw a graph of the function and calculate the area above the x-axis and count that as positive, and calculate the areas below the x-axis and count them as negative, and then add them all up, you will get the definite integral. Pardon me. Same as we did before with our rectangles, but it can be done with other straight line graphs as well. And curved graphs that you know what the curve is. So if you had something like a circle, you could go, oh, well, I know what the area of a circle is, and you could do that as well. So anything that you happen to know how to calculate the area by whatever methods you want, you can figure out areas. And so if I had a function like this, like that, and I told you that this was 1, 3, 5, and 6, and that this height here was, this depth here was -3, this height here was 3, and this height here was 1, then you could calculate the integral of this function it'd be this up area here, which would be a half of the base times the height, minus this down integral here, which would be a half of its base times its height, and plus half of this base times this height, and that would give you a total area, which is whatever it is. That would come out as a half, because this negative bit neatly cancels out this positive bit, and then there's a positive bit left over. So if it was based on areas of shapes you know how to find the area of, then you can do it. Not that your lecturer is probably going to do that, but I just wanted to point that out. It can give you a bit of a sense-making idea to be able to have a quick look at it and saying, oh, it spends more time above than below, so the answer should be positive. All right. So what Newton discovered back in the 1600s was 1600s, anyway, 400-ish years ago, was that you could do integrals by doing the reverse of derivatives. This was the fundamental theorem of calculus, and it says this. Give me one moment. So the fundamental theorem of calculus has two pieces, and the second part of the fundamental theorem of calculus, part 2, says that if you want to do the integral of a function from one place to another, then what you can do is try to imagine a function that differentiates to produce this answer, and then all you need to do is subtract that new function's answer at these two places. For f a function with its derivative coming out to the answer little f of x. So that's the fundamental theorem of calculus part 2, and what it tells you is how to do definite integrals using derivatives. You look at the function that is written here, you imagine something that differentiates to produce this answer, and then you subtract that thing at these two places. It turns integrals into a subtraction problem, which is much easier to do. So think of a function that differentiates to produce f of x and subtract two values of this function. That's the fundamental theorem of calculus part 2. In case you're wondering, the fundamental theorem of calculus part 1 says that fundamental theorem of calculus part 1 says that if you have a function and you do a running total area from one place to another, keeping track of the value of every area so far at every position, then what you create is a new function, and the derivative of that function is the one that you thought of first. So look at this. If I tracked the value of x along the x-axis here, and I did the running total of the area so far, if I was up to 6, the area would be 3. If I was up to 7, the area would be 6. If I was up to 8, the area would be 9. And every time I added 1, I'd get an extra 3 of the area. And so the area would be 3 times however far x is from 5. And so I would get this function that tells me what the running total area is so far. And if I differentiate that function, it'll produce this answer. So the slope of that is 3 because every time I add 1, I get an extra 3 area. and so the derivative is 3. Whereas this function would be a whole other thing. I would get the running total area here, would keep getting bigger and bigger and bigger and bigger and bigger, and then the area would start getting smaller and smaller and smaller and smaller and smaller, and then it would start getting bigger again. So if I create, given a continuous function, doesn't even have to be continuous, given a function that works, given a function f of x, yes, it does have to be continuous, sorry. Create the running total area function. This is what I call it. Which is going to be called today capital F of x, which is not necessarily the same as this capital F, which is starting at a particular spot, do the running total area so far up to the point x, like that. And so the picture that goes with that is this. Here's the point A, here's my function f. This is the t-axis. I have to change my variable so it's easier to keep track of what's going on. And then capital F has a running total area so far up to this point x. And so that area there is what capital F of x is. And then if I move the x a bit, I get a new answer for capital F of x, and that's the new function value. Yeah. So if you do create this running total area function, then the derivative of that function is the original function that you first thought of. And what this is saying is the rate of change of the area, how quickly the area is changing, depends on the current height of the function. The higher your function is, the faster the area is increasing at this moment. That's what that's saying. How quickly area changes depends on how high the function is. That's the idea behind it. The most important part of the fundamental theorem of calculus is this bit. But your lecturer has combined them all into one big theorem, but it's really important to know that that second bit is the most important part. Yep. All right. So what that means is, in order to calculate areas, if I don't already know the formula for it and I've got a curved function, what I have to do is imagine a function that differentiates to give the answer that I'm thinking of. So just giving an exact and full example of this. This here, the integral from 1 to 3 of 2x dx, that's saying, if I just imagine the picture that goes with that, 2x has slope 2 like that. Here we are at 1, and the answer will be 2 at that point. And here we are at 3, and the answer will be 6 at that point. And I want this area. So it should be possible for me to calculate this area just from this drawing, if I wanted, but I can do it using integrals. What I have to do is I have to imagine a function whose derivative is 2x. So I know that when I differentiate, the exponent goes down by 1, and I multiply by the current exponent. So I have to, if this was produced by a derivative, then it must have come from x squared. So when I do the derivative of x squared, it does come out to 2x, and so I can do this. And this is how we write the notation, like that. And the reason I do that is because I'm imagining that the derivative of x squared is in fact 2x, and so I can do this. And so I will get x squared with 3 subbed in minus x squared with 1 subbed in. So this bit here, that's this capital F of B minus capital F of A. That's what this bit here is. And this x squared here is my capital F that I'm talking about. And this 2x is my little f of x that I'm thinking about earlier. And so that would be 9 minus 1, which is 8. So this is straight up using the fundamental theorem of calculus in order to do this definite integral. How do you feel about that? Okay. Doing well. So just know that, again, the same deal happens, that if part of your function is below the x-axis, that piece will come out to be negative, but all of that is dealt with by this process. It doesn't make any difference whether it goes above or below the axis in order to use this process. It'll just all work out perfectly fine. So watch this. Give me a second. I am going to start at 0 this time. Let me do this function. I'm just going to have to figure out the formula for this function. Just give me a second. Yes. No, I'm just going to change this to a 6 just to make it my life easier. Goes across 3, goes up minus 3. Yep, okay. This is the function, that is this. And if I want to do this area, I know what this area is going to be, and I just want to point out that it's actually going to work perfectly fine. So I know, just imagining, this bottom negative area, it's got width 1 and depth minus 3, so its area is a half of 1 times 3, but it's negative. And this area is 2 wide and 6 high, and so the total area is minus 1.5 plus 6 is 4.5. That's what it comes out to. So I've got an area of 6 up here, minus an area of 1.5 here, and it should come out to 4.5 total. Okay, let's just see what happens. The integral from 0 to 3 of 3x minus 2 dx. I'm going to have to think of something that that differentiates to produce this answer. If it had been a 2x, it would have been an x squared in that spot. And so I need to put a number here so that when I differentiate this, it comes out to 3. I reckon 3 halves is going to be the trick. That'll do it. Because then 3 over 2 times x squared, if I differentiate that, I'll get 3 over 2 times 2x, which will be 3x. And then if I differentiated something and it got a single number, that would have been something times x. So this would be minus 2x, like that. And so this will produce 3 on 2 times 3 squared minus 2 times 3. That's what I get when I put the 3 into this. Minus 3 on 2 times 0 squared minus 2 times 0. That's what I get when I put the 0 into this. And I get well, this is bad. I think I've done something wrong. Well, let's see what happens. So 27 on 2 minus 6 minus 0 27 on 2 would be 10, 13 and a half. I get 7 and a half. Damn it, what have I done wrong? I hate it when this happens in a revision seminar because it doesn't make the point I want it to make. Which is 4 more than I expect it to be. Kara says. That's okay. We can deal with these things and figure out what I did wrong. It could be anywhere in this process. Let's just see. So 3 times 0 minus 3 is indefinitely that number. 3 times 3 is 9, minus 3 is 6. Okay, so this really is the function I want. And just check, when x is 1, it does come out to be 0. Okay. A half, the base is 1, height is minus 3. So that's minus 1.5. Base is 2, height is 6. All right. Just going to ask Desmos what this is for a second. I've got a whole different answer again. Oh, 0 to 3. No, it really should be 4.5. So what have I done wrong here? Ah, it's 3x minus 3. I copied it down wrong. I wrote 3x minus 2, but it's 3x minus 3. That'll be 3 times 3, which is 9. Which is 4.5. Exactly as it was supposed to be. All right, cool. The point I was trying to make is that you don't have to deal with which bit's negative and which bit's positive. The formula deals with that all by itself. My general advice for exams, and I really should have done it, I should have checked to see if I copied the function down right when I did the integral. Rookie move, David. Okay. So it's really hard work to try and imagine functions that differentiate to give these answers. And so what we normally do is have a list of how to do it. Instead of, we remember how to create a function that differentiates to give the answer I'm thinking of, rather than trying to do derivatives backwards. That's quicker. And so the rules are these for polynomials. Whoa, wait just 1 second. I will just tell you what I did there. There is a rule that says that when you look at a power of x like this, x to the power of 1, if you were differentiating, you'd multiply by the current exponent and you'd make the exponent go down by 1. When you're integrating, do the opposite. You put the exponent up by 1 and you divide by the new exponent. So that x squared, x went up to an x squared, and then I divided by the 2. And if you see a constant, you attach an x to it. And unfortunately, the quickest way of being good at integrals is to remember those things and keep practicing remembering them. And I have one last thing to say. It would be really cool if there was a notation for what this function here is. When you imagine this capital F in inverted commas function, you need to know, it would be really cool if there was a notation that says, what is this function? And there is, and what we do is we remove the numbers, and that's what it means. So when you see something like this, this is a representation of all the possible functions that differentiate to give f of x. Well, maybe not all, but any possible function. It's just one of them at a time. So they call these things antiderivatives because they're derivatives backwards. And they also call this the indefinite integral. And because it's supposed to cover any possible function that differentiates to give this thing, when I write this notation, I have to put a plus c in. So for example, I used one already. When I had the 2x dx, if it was a 1 to 3, I put square brackets in like this. But if it didn't have the numbers there, I would just write x squared. And what I would do is I would put a plus c here, because if I had put x squared plus 1 in this spot, it would have worked out to the same answer anyway. Because I would have had an x squared plus 1 minus, like a 3 squared plus 1 minus a 1 squared plus 1, and the plus 1s will cancel out because we're subtracting one from the other. So that's the difference between them. This is a definite integral, this is an indefinite integral. This is a number. This one's a number. This one is a function with a plus c on it. And that's the difference between them. And this is a way of me figuring out what needs to go in this spot to do the integral I need. And the reason we have this notation is that there are some clever tricks called integration by parts and substitution or variable change that allow us to fiddle with this notation and figure out an answer to go here. How you doing? Okay. So when people try and write what should go in this spot, they tend to write this instead. Basically, that's the short version of it. So some rules for how indefinite integrals work. So the rules for indefinite integrals go, there's two parts to the rules. One part is a list of things that you know how to integrate, and the other part is a list of strategies for splitting up functions into smaller pieces, basically. So there's a list of things you know. So for known integrals, these are our known integrals. The integral of x to the power of, well, the integral of just a plain number I'm just going to call it B, where that's just a plain number. No, I'll call it C. No, I've already used C. A. The integral of just a plain number will be that number times x plus your C. When you do a definite integral, you won't need the plus C. So just as an example, the integral of 5 dx is 5x. Yep. And the integral of 1 dx is just 1 times x. So that's our very first and most basic rule. And that's what I said right at the beginning, that the running total area of a constant function is, well, it's the height times the distance you've gone so far. So that's our first one. Our second one is that if you have just x, that integral is a half of x squared. And if you have x squared, that integral is a third of x cubed. And if you have x to the power of cubed, that integral is a fourth of x to the power of 4. So what that means is that you put the exponent up by 1 and you divide by the new exponent. It even works for negative powers. The exponent went from -3 up to -2, and then I divided by the new power of -2. The exponent went from -2 up to -1, and then I divided by the new power of -1. So all of these are examples of the same thing, that if you see x to the power of number, then you put the exponent up by 1 and you divide by the new exponent. Like that. All right. Cool. So far, that's great. How are you feeling? Okay. So this is enough for us to figure out what the integral of any polynomial is. Polynomial being thing made from powers of x, and even things that are, I don't even know what that is, that's like a rational function. And that's because there's another rule, these are known integrals, there's another separate rule for joining integrals together to make functions together and seeing how their integrals change. So I'm just going to make a gap in my notes. One second, I'm just going to check. Something. Yep, okay. So I'm just going to leave a little space because there's 2 more integrals to do just here of known integrals that you're supposed to just remember. Okay. And we're going to have some rules for making new functions from old and what that does for integrals. So when you're making new functions, if you add two functions together, then you add the integral as well. So this is the long version, the fancy version of it. That integral is the same as this. So you can do algebra on it. You can bring the integral sign in across a plus. Also works for a minus. But in practice, most people never write what I just wrote. They write something else, but I'll do that in just a second. Actually, I will do it now. So for an example of that, the integral of x plus 5 dx, well, since they're added, I can do them separately. I will get a half of x squared, and I'll get a 5x, and I'll just whack a big plus c on the end. And technically, you'd expect there to be a plus c from both of them, but it doesn't matter. Most of the time we play fast and loose with that, and we just pretend that it's just any old function that would work to differentiate to produce either of these, and then we put a plus c on the end. So normally we don't actually explicitly write the move where we go, well, this is the integral of x dx plus the integral of 5 dx. We just do them separately. So that's that rule. But sometimes we do use this if we're doing things with algebra. And the other rule is that if you multiply by a constant before you do the integral, then that multiplied by the constant will still be there after you do the integral. So the algebra version of it is this. Where you can bring a constant multiple in and out of the integral sign. That's the algebra version. But most of the time, it just looks like this. The 6 is multiplied by the x cubed, so things that are multiplied on before will still be multiplied on afterwards. And then the integral of x cubed is x to the power of 4 times a quarter. And so I'll get 6 divided by 4 is 3 over 2. So this is what it normally looks like in practice. Some people, if they have the presence of mind, are able to do all of that in one step. I'm not, but other people are, where if you had something like that, then you could go, all right, you could imagine the 18 is still there, multiplied on, the x squared would become an x cubed, but I'll have to times by a third, and 18 divided by 3 is 6. So some people are able to do that all in one go, see the 18x squared, go, I'll have to put the x up to 3 and divide by the 3, and 18 divided by 3 is 6. So you are allowed to do that move, if you like, all in one go. So these are the two main rules for how integrals interact with each other. There is no quotient rule or product rule. Well, there's no quotient rule for integrals. So you definitely cannot just do the two integrals and multiply them together if they're multiplied separately. Okay, so you can't just, if you had f of x times g of x, you couldn't do the two integrals separately and multiply them. That is not how integrals work. They only interact well with plus and times by a constant. And what this means is that you can now combine these two together to do any polynomial. Even better, you can now, no, that's all right. do something like this. Go, cool, 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 cool. 6 is multiplied on, it will still be there afterwards. Just to be absolutely clear, this 3 divided by x squared is the same as 3 times x to the power of negative 2. Like that. And so 6 is multiplied on, so it'll still be there afterwards. X goes up to x squared, but I have to divide by the 2. The minus 3 is still there. The x to the power of minus 2 goes up to x power of minus 1, and I'll have to divide by the minus 1 plus c. And so I get 3x squared minus 3x to the negative 1 plus c. How do you feel? Okay. So that's great. And I've already used a technique there that is really worth noting, that you can rewrite the integral first to make it into a format that you know what to do with. I don't know how to integrate 1 on x squared, but I do know how to integrate x to the power of negative 2. So that's one of our first techniques, which is rewrite it. I'm going to go back here and add 2 new pieces to our list of things that we know how to integrate. The integral of e to the power of x dx is exactly the same as it was before. Just looking on my thing. Okay. And what if it wasn't the number e? What if it was some other number? If you had the integral of 3 to the power of x dx, that would be 3 to the power of x, but I would have to divide by ln of 3. And if it was 4 to the power of x dx, it would be 4 to the power of x, but I would have to divide by ln of 4. And so the combined rule is that if you see the integral of number to the power of x dx, you'll be exactly the same as it was before, but I will have to divide by ln of that number. And it works for this too, because ln of the number e is 1, and so I'm dividing by 1 when I do this integral. Okay. Okay. So that's our basic rules. So now, that's great. That allows us to join integrals together by addition and subtraction and multiplying by constants. We can integrate all polynomials now. We can even integrate the square root of x because we can rewrite things. I'll show you that in a second. Anything that can be rewritten into those formats, we can now do. Cool. So there is one more technique that I'm going to put now that I put at this level of the just do it level because you just know the answer. And your lecturer will put it slightly later, but I don't think they'll mind. So let's do this now. So this is the rule. It's difficult to describe. If you know the integral of f of x dx, and it comes out to capital F of x plus c. If you know that already, and what you have is not f of x, but f of ax plus b, then you would do what you would normally do if that was an x. But it's not an x, it's an ax plus b. and I will have to divide by that a that's next to the x there. I call this in my head divide by the constant derivative. The reason this works, well, I'll do it with an example. That integral, I would know what to do if that was just x to the power of 5. If it was x to the power of 5, the answer would be x to the power of 6 times 1/6. But it's not an x, it's a 3x plus 1. So I'll have to, and the derivative of 3x plus 1 is 3, which is just a plain number, so I can divide by that number, which is the same as multiplying by a third. That's how to use this rule. And the reason it works is that if I differentiated this function, the 18 would still be there. Oops, sorry, this is plus c. If I differentiated this function, I'm just going to imagine that derivative. Then the 1 on 18 would still be there, and I'd multiply by 6 because of the chain rule. And then because of the chain rule, I would have to multiply by the derivative of this, which is a 3. And now look at that. That 1/6 that I had before, look, that 6 times 3 is 18, and it cancels with this 18, and we end up with what we started with originally. And that always happened. This 1/3 is the thing you need to put there to cancel out the 3 that will appear if I did the chain rule to get back, to do this backwards. That's the idea behind this rule. And one of the most important times to be able to do it is when you see this. Like that. If that had just been an x, the integral would be just e to the power of x. Exactly as it was. That's what e to the power of x does. It doesn't change when you integrate it. But it's not an x, it's a 5x. And so I'm going to have to divide by the 5. This is this rule in action, and you're allowed to just do it. How's that for you? Okay. Right. So now I can do many things. Even things that I don't think I can do, because I can now get into the techniques of integration. So the techniques of integration are these. Technique 0 is just do it, which is all the things I've mentioned so far. Just straight up do it. Go straight from e to the 5x to 1/5 of e to the power of 5x. Go straight from x squared to a half of x to a third of x cubed. Just do it. It's not even a technique, which is why I call it technique 0. But it's really important to remind yourself that there are lots of integrals that you can just do, and there's nothing really special that you need to do. You just do them. Technique number 1 is that you need to maybe rewrite it. And in a minute, I'm going to put some things here. There's a technique 2 and a technique 3. Okay? I'll get to there. Because I want to give some examples of rewriting. And it's just easier to do some examples. This one, I can't use that divide by the constant derivative trick because the derivative of the thing inside here isn't a constant. The derivative of that is 2x. And I can't just divide by a 2x. I can only divide by that thing if it's a constant, and it's not. So in my head I'm going, the derivative of the inside is 2x, which is not constant. Damn. So I can't just do it. But I know that I can integrate any polynomial, so I can expand this out. So let's see, I'll get x squared plus 2 of x squared plus 1. Because if that was just an x, when I expand it out, I get x squared plus 2x plus 1. But it's an x squared, so I'll pop that in there. And so that's the integral of x to the power of 4 plus 2x squared plus 1. And those things I can integrate. The integral of x to the power of 4 is x to the power of 5, but I have to divide by the new exponent. The 2 will still be there. And the integral of x squared goes up to x cubed, and I divide by the new exponent. And the integral of 1 is x. Yay. I was able to do it by rewriting it. Oh, just a second. I missed one of the classic integrals before. I've just realized something. I missed one of the integrals on the list. I'm very sorry. And the reason I knew that is because of this. So I'm just going to have to slip it into my notes here and put an extra page in just here. I will send you these notes afterwards, by the way. There's one more classic integral, and I just want to point something out here. When I did these, there's only one of them that's not going to work. If this was already x to the power of negative 1, the exponent would go up to 0, and then I'd have to divide by 0, and I can't divide by 0. And so the x to the power of negative 1 doesn't work with this rule. This doesn't work when this number n up here is negative 1. It works for every other number. And there is a special rule just for n being equal to negative 1, and it is this. That one, it's normally written like this instead. Most people see it this way first. And if you see 1 divided by x exactly written that way, then the integral is ln of the absolute value of x plus c. And you need the absolute value just in case when you do the definite integral, the inputs are negative. Yep. That is your last integral that we just know. I'm glad I remembered it before I moved on too far from where I was. You okay with this integral? All right. So just to summarize, we know what to do with 1 on x, which is the same as x to the negative 1. We know what to do with x to any other power, and we know what to do with number to the power of x. And they are different. Just look how different these are. X to the power of number still looks like x to the power of number afterwards. And we adjusted what this number here was. Number to the power of x still looks like the same number to the power of x. And the x doesn't change at all. And neither does this number. All we do is divide by something. So really important to distinguish between those two. Okay. Back to where I was. I was rewriting this. This thing, it's not currently in a format that I can use. There's no rule for division, but I can divide both of these by x. Which is the same as x plus 5 times 1 on x. And that integral is fine. The integral of x is 1/2 of x squared. And the 5 will still be there because it's multiplied on. And the integral of 1 on x is ln of x, the absolute value of x. Yay. So that's the rewrite it technique. It's almost never a bad plan to try to do that. And there are lots of ways of rewriting things that make them easier to do. I'm going to do one more example, which is my favourite, which I've done in a previous revision seminar, but I love it so much. This integral, theoretically, I could expand this out. I do not want to because it's going to have a lot of pieces. But I can do one other thing. If this x had been an x plus 1, then I would have been able to just multiply the x plus 1 by this x plus 1 to the power of 15 and get x plus 1 to the power of something. And so I can rewrite this. I can say, well, if that x had been an x plus 1, that would have been great. But I'm just going to make it more like x plus 1. This plus 1 minus 1 inside where this x is hasn't changed this function. Do need to put the dx on the end, that's really important. It makes a difference for later things. That hasn't changed this function. But now I can see an x plus 1 and I can see a 1, and they can both be multiplied by this thing. So that's going to give me x plus 1 times x plus 1 to the 15 minus x plus 1 to the power of 15. Oh, cool. That is x plus 1 to the power of 16 minus x plus 1 to the power of 15. And those I can do because the derivative of the thing inside the brackets is a constant. It's actually the number 1. So that integral, if it was an x, would be 17 and divide by the 17. But it's not an x, it's an x plus 1. So I'll divide by the constant next to the x, which is a 1. And this integral would be 16 with 1/16. And it's not just an x, it's an x plus 1. So I'll have to divide by the derivative of that, which is 1, and so that's fine. And so here is my final answer, and it's really cool. It's one of my favorites. Yeah. How do you feel about that one? Cool. Thanks for bearing with me with the how do you feel. I just need to check in with people every so often. Don't like to talk for too long without asking people how they're going. Okay. And now we are up to the final techniques. And I will go over, if you have to leave, then that's fine, but I'm just going to keep talking until I get to the end of it, whether you leave or not. So, all right. So that was technique 1, which was rewrite it. And sometimes if you factorize it, it'll be easier. There's no particular rules for how to rewrite it. You just trust that it might be possible to do. The second technique, or technically the third, but technique number 2 is what most people in the world will call substitution, and your lecturer calls change of variables. So if you want to find examples of this thing in your notes online, look for substitution for integrals, and you will find lots of information. The change of variables technique goes, well, what would you do if this wasn't, the derivative of that bit wasn't a constant? And the rules say that you can do it as long as the derivative of this thing is already there. Yep. Okay. So, if, this is what your lecturer said, if you see an integral where there is one function inside another function, and the derivative of this function is already there, then, nope, the integral sign goes away. Then you can pretend to integrate this the way you would normally integrate it. So crap ass, sorry, one moment, I'm going to rewrite it. I will write that line that I just wrote, but I want to write it again. If the integral of f of x dx would become capital F of x plus c, then the integral of f of some other function times the derivative of that function, it has to already be there, is this. So if you would know what to do if the thing in here was an x, but it's not an x, it's some other function, you can do what you would normally do, but only if the derivative was already there. And the reason is, if I differentiate this, this is an antiderivative. If I differentiate the capital F, I have to get little f. If I differentiate this, I'll get little f, but then the derivative of g will come out because of the chain rule. So this is what your lecturer says. And so knowing this fact, if you can rewrite it so that it looks like this, then you can do it. Most places in the world have a way of doing this using the letter U traditionally, but I'm not convinced your lecturer does it that way. So I'm going to attempt to do it and ask you how it's done in your course. So, this integral, I can see that e to the power of 1 minus x squared is a problem, because if it was just 1 minus x, that'd be okay, because the derivative of that is a constant, and I could just divide by that constant. The x times by this is freaking me out a bit, but just focusing on the function that's inside the function, I can see that this has got a 1 minus x squared. The derivative of that is minus 2x. And what I have multiplied by here is nearly minus 2x, except for being the wrong constant. So this is what I'm imagining here. The derivative of the 1 minus x squared will be a 0 minus 2x. And this is nearly what I do have here, this x. So I'm going to move this x over here and have an x dx. It's nearly right. It's just got slightly the wrong number. And so what I'm going to do is fiddle with the numbers so that it is the right number. So I'm going to say that x is the same as this. Like that. And I need this to be a minus 2x and not an x. And so I'm going to multiply by minus 2 and divide by -2, like that. So I haven't really done anything. I've multiplied by -2 and divided by -2. Nothing's actually happened, but what I can notice now is that a constant multiplied on will still be there afterwards. And without that, it's e to the thing times the derivative of thing dx. And so using a change of variables like your lecturer did, I can see this as e to the power of 1 minus x squared. I have a question. Is that, this move of adjusting the number, is that how your lecturer did it? If you don't know, that's okay. Not too sure? That's okay. How do you feel about this move that I made? Okay, cool. I'm just going to show you how this would normally look if you looked it up on the internet. If you Googled if you put this formula into something like Wolfram Alpha or Stack Exchange or something, they would show you a different method. And I just want to show you what that method is, just so that you've seen it, so that you don't freak out if you see it in the future, or if one of your lecturers in later courses does it a different way. Okay. So looking at this, I can see that there is something inside this other function, and what I'm going to do is I'm going to call that u. And then I'm going to differentiate this, because I'm pretty sure that this x is nearly the derivative of that. So at the moment, it's very similar to the working I did earlier. Instead of just doing d on dx of this thing, I've given it a name so that I can do the derivative this way. And then I know that when I do integration this way, I need the derivative times dx in order to do this process. So when you look at the way this formula worked back here, I need the derivative of the inside times dx. So that's du on dx here. So what they do is they pull a Swiftie like this, is they say, they split the du and the dx apart like this. And they say, I can see an x times dx in my original formula, which is, I've got the x times dx, and I'm going to move that -2 out the way. And then when you look at this function, this bit is what u is. And this bit was -1/2 of du. And now my x's have gone away. That constant is multiplied on, so it will still be there afterwards. The integral of e to the power of x would be e to the power of x, but it's a u, so it's e to the power of u. And then I can put my u back in and sub the x's back in again. I just wanted to show you that this is how the process normally works. If you wanted to look up this integral, this is what would happen online. But it is totally okay to use, and it's probably better in your course to use this one. To say, I notice that the thing that is here is nearly the derivative of that, except I'm off by the wrong constant multiple. And so what I'll do is I'll divide by the constant multiple I want and multiply by it so it all figures out in the end. But I just wanted to show you the alternative working. Okay. So there is one classic example Oh, not a double integral. What are you doing, David? Something like this. This one's particularly tricky. So when I look at this, the worst part of this function is the fact that there is something in the denominator. So I'm going to look at that denominator and I'm going to think the derivative of the denominator is 2x plus 6. And if I look very closely, that is 2 times the numerator. So let's just work this out. Now separate this out. This x plus 3, x plus x squared plus 6 as a fraction, I mean, if this had been a 7, it would be x plus 3 sevenths, is 1 x plus 6, x squared plus 6 times x plus 3. And I really want that to be a 2x plus 3. So I'll do this. And now this is the derivative of that. And so I can call that my g of x in the way the formula works. So the half will still be there. The integral of 1 over, if that was an x, it would be 1 over x, and so that would be ln. And this disappears by virtue of it being the derivative of that thing. Ta-da. How do you feel about that piece of working there? Okay. Right. So this, many people who do integrals actually put this thing that I just did where there's a fraction way back up to the just do it category. If you see the derivative of a thing on the top and the thing on the bottom, that'll automatically become ln of the thing. And this is because of this change of variables rule. Because f dash x dx is the thing you would normally see if you were doing change of variables and you have 1 over that thing. Yeah. So a lot of people who do integrals a lot remember this rule all the way back in the just do it category. Just going to pause the recording for a second. The last technique number 3 here, is integration by parts. And integration by parts is trying to be the product rule for integration. So you know how I said that there isn't a rule for integrals for when there's two functions multiplied together? There is, it's called integration by parts. But it only works if one of your functions is already the derivative of something. So if you see two functions multiplied by together, the first thing you should check is if one of them is the derivative of the inside of the other function. And that's how the change of variables works. With integration by parts, they're not necessarily related to each other. So if you see two pieces multiplied together and one of them is the derivative of part of the other, that's when you do change of variables. If you see two functions multiplied by together and they're not really related, that's what integration by parts is for. And integration by parts goes like this. I'm just going to check how you're... It's designed to have two pieces multiplied together inside the integral sign. And this is going to become this new expression, which will not be done yet. Okay. This is not correct yet. The only way the integration by parts works is if you imagine one of these functions as already being the derivative of another one. So it will be something like, there'll be a dash here because you're imagining this function as already being a derivative, and the other one will have a dash over here. So integration by parts doesn't do the integral for you. It just turns it into another integral that you hopefully know how to do then. I will say something. It works the other way as well. So it doesn't matter, you could have this one being a dash, and at the end the other one's a dash. Or it could be the first one's a dash, and at the end the second one's a dash. Doesn't matter. Maths works the same, multiplication works the same whichever way around you write it. It works fine. These are the integration by parts rules. And you have to decide which one is going to be the one that you imagine being a dash. And that decision has to be based on you being able to integrate that thing. So this is your choosing the dash. So choosing the one with a dash or a prime, if you like. You have to know it's integral. So if you don't know how to integrate it, it can't be the dash. And the one that doesn't have the dash is going to get a dash later, and it needs to get simpler when you differentiate it. Okay, that's how you make your decision of which one has the dash. So let me show you an example of that. Sorry, the drop-in centre people aren't checking the Zoom, so I'm just checking on them. This function, for example, is two things multiplied together. X is not the derivative of the thing on the inside, and so I can't use change of variables. And it is two things multiplied together, which is exactly what integration by parts is for. I can't rewrite it, so it's not going to work. I'm just going to have to run with this. So let's see what happens if I call one of these u and the other one v. And I find the easiest way of dealing with this is actually to write this down. I'm going to call this one x and this one ln of x, and I'm going to have to choose one of them to have a dash, because what's going to happen is that the one with the dash is going to become integrated on the next line. So I can't choose this one to have the dash because I don't know how to integrate ln of x. I don't know how to integrate that, but I do know how to differentiate it. So this ln of x, I would like to differentiate it by the time I get to the end, and this u is going to be the one that's already got the dash. So I've chosen that u dashed of x is x, and that v of x is ln of x. That's what I've chosen here on the first line. This one is x, this one is ln of x. And I've written them underneath each other so that I know which one goes with which. So this u of x, the dash is gone, I'm going to have to integrate. And so the u of x will be half of x squared. So that was an integral. But the v dash, by the time I get to the end, will be the derivative of this, which is 1 on x. So this is the derivative. The differential way, differentiate. And so the u here is a half of x squared. The v is still the same as it was originally, so that's still ln of x. The u is still half of x squared. And the v dashed is 1 over x. And now what my integration by parts has done is it has turned my original integral into a new integral that I still have to do. So I'm going to pretend that this didn't come from any of this. I'm just going to look at it and see what happens. I can simplify that, I can rewrite that, and hopefully I'll know what to do. X squared divided by x is x. And I do know how to integrate x. It's a half of x squared, and the half will still be there because it's multiplied on. And the moment the last integral sign disappears, that's when you put the plus c in. So this thing is the integral of this thing. How'd that go for you? This half here, if that half there, or that one. That one there. So this half is that half that's already there. And this x became this half of x squared. Yep. Good question. So, yeah, the half that was already there is still there, and then this x became a new half of x squared on top of the half we already had. Okay, so that is how integration by parts goes. But you can combine any of the things we've done before with integration by parts. Something like this, which is horrible, by the way. It's going to be bad, but we'll cope. We'll cope just fine. Just so that it's a little easier to cope, I'm going to make this a 6. Okay. Okay. So it's two things multiplied together. This is definitely not the derivative of that. And so I'm going to use integration by parts. So it's going to be 2 parts multiplied, and that is going to become the same, the thing without the integral sign minus a new integral. But one of these has to have a dash here, and the other one has to have a dash here. If this one had a dash, if this one had a dash, I do know how to integrate that, and I do know how to integrate this too. But if I integrated this one and differentiated this one, when I differentiate the e to the power of 3x, it's still got an e to the power of 3x in it. That's how e to the power ofs work. And it's not going to get any better. It'll always just, if I differentiate it, it's still the same, and then this getting integrated would go up to x cubed, and that would be worse. And so I can't make this one, the one with the dash, because this one, when it gets differentiated, doesn't get any better. So I'm going to make this one the one with the dash. And the reason I've done that is if I've got u here, when I differentiate that, that'll become something with, it had an x squared and it'll have an x by the time you get to here, and that's just a little bit simpler. So that's what I'm going to do. So I'm going to say that u of x is 6x squared, and v dashed of x is e to the 3x. And so I'm going to have to differentiate this one because it doesn't have a dash yet. And that'll be 12x, because the 6 will still be there and I have to multiply by 2x. And then this v dashed will have to become a v of x. So I have to integrate. When I integrate e to the 3x, it's still e to the 3x, but because of the divide by the constant derivative integral rule, you'll have to divide by that 1/3. If I was differentiating, I'd multiply by that 3. So I did a derivative here, differentiate here, and I integrated here. That's what I did. Okay, so now I know that this ux is still a ux afterwards, and so it's still going to be 6x squared. This v dash has become a v of x, which is now 1/3 of e to the 3x. This u dashed, this is now u dashed, which is 12x. And this vx is still 1/3 of e to the 3x. And so I get 2 of x squared e to the 3x minus 4x e to the 3x. And as always happens with integration by parts, I haven't finished yet. I've still got an integral to do. Problem, this is still not the derivative of that. I'm going to have to do integration by parts again. Now I've already used u and v, so I'm going to give them new letters. V, W, oh crap. How about S and T? No, I don't like that. Let me call them F and G. And so the integral of f of x gx, one of them will have a dash when I do this, will be f(x)(gx) minus the integral of f(x)(gx), because that's how integration by parts works. One of these will have a dash here and the other one will have a dash here. Same problem's going to happen. If I integrate this one, it'll just go back up to x squared, and I only just came from there, and so I'm going to make that one have a dash later. Because 4x, when I differentiate it, will become just the number 4, and numbers are great. Plain numbers are great for integrals, so I'm just going to leave it like that. And so I've got that f of x is 4x, and g dashed of x is e to the 3x. I'm going to have to differentiate that one because it doesn't currently have a dash. I'm going to have to integrate this one because it currently has a dash and I want that to go away. So e to the 3x, when I integrate it, would still be e to the 3x, but I have to divide by the 3 because I'm integrating. And so I get 2x squared e to the power of 3x minus f of x is 4x, g of x is 1/3 of e to the 3x, minus the integral of f dash of x, which is 4, and g of x, which is 1/3 e to the 3x. And I'm still not done. I've still got another integral to do, but it's okay. This is 4/3 times e to the 3x. I can do that. So the 4/3 is a number which will still be there afterwards. And the integral of e to the 3x is 1/3 of e to the 3x. And now that the last integral sign has gone, I can put my plus c in. So my final answer is 2x squared e to the 3x minus 4/3 x e to the power of 3x. And then minus minus would be plus, and that's 4/9 of e to the 3x. Oh. How'd that go for you? Yeah. Which bit of this was the most confusing? That's okay. That's fine. It's a long process. I find that writing down them underneath each other and writing down what each bit is helps me to focus when I do it. And there is no shame in doing that during an exam. Especially you should do anything you can to make sure you get it right. I would not like, I would have feelings about a person who puts an integration by parts that requires 2 integrations by parts to do it in an exam, but I don't know. That's I have no idea what they're going to do. Those are the techniques of integration. Those are the techniques of indefinite integrals. And I put them in this order, the order that I put them in, because it's the order you should try them. So if you are trying to decide how to do an integral and the person doesn't tell you how to do it, then this is the order to think about it. You'll stare at it and go, can I just do that? Like, is it something I already know? Or, oh, if I rewrote it, would I know how to just do it? Or is one bit of it the derivative of some other bit? Maybe I could change the variables. And then after that, you go, all right, is it 2 things multiplied together? Ah, cool, I can try to do integration by parts. And if all else fails, well, you haven't been taught techniques to do those things. And so you would ask a machine to do it for you probably at that stage. There are other techniques, but this is where we are at the moment. Right. So, last thing, they are all the techniques of finding out definite, indefinite integrals. One of the main purposes of finding indefinite integrals is to find definite integrals. Give me one moment, I'm just going to check something in the notes. Okay. So there's one thing I didn't put, which is that definite integrals have their own extra properties that indefinite integrals don't have. So back here, these rules of splitting up indefinite integrals, they work just as well for definite integrals, but there's a couple of extra rules which are really interesting and useful. I'm going to do one more. I'm going to do just one more example of using indefinite integral techniques to do definite integrals. Let me do this one. The integral from 0 to ln of 2 of e to the power of x over e to the power of x plus 1 dx. This one's complicated, it looks complicated, but we have the techniques to do it now. So I can see that it's a definite integral, I'll deal with that later. First I'll do the indefinite integral. Okay. The only way to do a definite integral is to figure out something whose integral is this. And so I'm going to do that part first. All right, my techniques of integration say I can rewrite things. All right, with a plus on the bottom of the denominator, it's really not going to be able to be rewritten in any particularly useful way. And the next thing would be to see if one part of it looks like the derivative of another part. Well, the derivative of the bottom is e to the x. I can do that. The derivative of e to the x plus 1 is indeed e to the power of x. I have a thing and its derivative on the top, so I can use the change of variables process. So I'm going to rewrite this integral so that it's easier to tell that it's a change of variable situation. Like that. And this is the derivative of that. And so what that means is I can pretend this is an x, and the integral of 1 over x would be ln. And I'll get that. Cool. And so, therefore, the integral from 0 to ln of 2 of e to the power of x over e to the power of x plus 1 is this thing that I just figured out from 0 to ln of 2. Which means I need to sub in both of these numbers and subtract the answers. So I substitute ln2 into this formula, I substitute 0 into this formula, and I have to subtract the top one minus the bottom one. Well, e to the power of ln2 is 2. And e to the power of 0 is 1. And ln of the absolute value of 3 is the same as ln of 3. And that is my answer, ln of 3 minus ln of 2. So I could, if I wanted to, get my calculator and ask what that was. ln of 3 minus ln of 2 is 0.4055. Approximately 0. There you go. Do I expect this answer to be positive? Yes, I do. E to the power of x can't be negative. So both the top and bottom are positive, and so this is a positive number. When you integrate a positive function, you have to get a positive answer, so I do expect the answer to be positive. Didn't quite expect it to be such a small number, but I guess when x is 0, it starts at a half, and then it only gets smaller, I reckon, and so, yeah, it's not that, that's fine, it seems reasonable. So one last thing. Couple of extra rules for definite integrals. We had these rules already, that when you add beforehand, then you can add afterwards. It doesn't matter. The same thing happened with other integrals, and it also means that by the same token that if you have a constant times your function, then you can multiply it before, you can multiply it after, it doesn't matter, you'll get the same answer. We had those rules before. But there is a couple of other rules that are important to know. Basically, one other rule. Two other rules. And the rules are about not manipulating the function, but manipulating what's here in the limits. So if you go any function from one number to the same number, the answer will be 0. And the reason for that is that if you have a function, here you are at A, the area from A to A is nothing. It's just a really skinny line, nothing at all. There's no running total there at all. There's no area. And the integral from A to B of f of x dx is the same as minus the integral from B to A of f of x dx. So this one's unexpected. That's saying that if you do the integral this way from A to B and you get a positive answer, then if you do the integral this way from B to A, you'll get a negative answer. And you know how I said it was an area? Well, it's not quite, it's a running total. And so if I'm doing a total, adding up extra little bits as I go along, well, coming backwards is the same as subtracting little bits as I go along. That's the idea. Because I'm going in the wrong direction, I'm doing a running subtraction as opposed to a running total. That's why. So this is positive, this is negative because it's going the wrong way. And the last thing is that if you do the integral from one place to another, it's the same as if you do it from one place in between and then do it from the in-between place to the last bit and add the two answers together. And that's this. If you're going from A to B, it's the same as going from A to C and then from C to B. And what that means is that even if you didn't know what the function was, you could get some cool stuff going on. Watch this. Suppose the integral from f of x dx was 8, and the integral from 3 to 7, and the integral from 7 to 8 of 5 f of x dx was 20. What is the integral from 3 to 8 of 2 f of x dx? Not that anyone would want to know such a thing, but it's just a fun puzzle you can do if you know how to do these things. So the first thing I notice is that this 5 can come out. Multiplying by 5 first is the same as multiplying by 5 after, which means that the integral from 7 to 8 of f of x dx is going to be 20 divided by 5. And this thing here, that's just a number. So 5 times some number is 20. That means that that number must be 4. And now I know what the integral from 7 to 8 is of f of x, and I already knew what the integral from 3 to 7 is. If I want to go from 3 all the way to 8, well, I could go to 7 and then go to 8, so I could add them together. So in my head, I've got from 3 to 7 and from 7 to 8, and I'm adding together those two pieces. Not that I know what the function looks like. And so that would be, this answer was 8, and this answer was 4, and so I get 12. But what I wanted was the integral of 2 of f of x, but that's okay. The integral of 2 lots of f of x should be twice as much. Ta-da! So no matter what the function is, if those are the answers that it gives, then I can figure out what's going on at other places. I think that'll do for today. But before we sign off, how do you feel about what just happened there? Cool. Do you have any specific questions about integrals that I didn't talk about that you want me to talk about? Cool. Anything stand out there as particularly helpful? Like in the whole hour and a half or 2.5 hours or whatever it was? Thank you. Humans do not learn by algebra. They learn by example. So it can help you make sense of what the algebra is doing. So I'm really glad that you appreciated that. All right, I'm going to sign off the recording and